Welcome and thank you for joining us in digging deeper into the version 9 of the Australian curriculum, years 7 to 10. In this session, if you haven't seen the other three, we're session number 4. The other sessions are available for you online for you to go back and review. Sarah and I will be your presenters today. Sarah, would you like to introduce yourself?
Sure, yeah, I'm a senior educator and my experience is mainly senior school. I've taught IB computer science and before that I worked as a software engineer.
And I'm Kylie, I'm a lead educator, and my experience is mainly in Queensland, digital technologies, digital solutions, design technology, and we're really happy to be here today and to go through the curriculum with you. So a rough look at the schedule for today. We've got a little bit of recap of what we went through last week in Algorithms Part 1. Have a look at a little bit about the meaning of the implementation, nested control structures, logical operators, a little bit of debugging, and a bit of a dive into pedagogies that can be used for programming. So a short recap of Part 1 algorithms. We looked at the differences between version 8.4 of the curriculum and version 9. And one of the main differences was the introduction of the terminology of flowcharts and pseudocode to be used by students in years 7 to 10. So previously, I think it said something such as to be written in English and diagrammatically, whereas now it's specified. Also, the changes in user experience to modify designs and specifically to prototype in years 9 to 10. So there were some significant changes there and clarification to the curriculum, worth looking at Algorithms Part 1 if you missed it. So an overview of the session today is that we're hoping to look at the major differences between 8.4 and 9, explain ways to address the content descriptions, identify links to the general capabilities where we see them, demonstrate some examples of ways that you could implement this into the classroom. And we've got a few little resources along the way that might assist. And we'll go through Algorithms Part 1, implementation, debugging, and some pedagogies along the way. So the process of digital solutions, creating digital solutions according to the curriculum, it's a circular motion through defining, designing, implementing, and evaluating. At the moment, we're looking at implementing. Last week, we looked at designing. So most of what we look at today is at this stage, if you can keep that in mind while we're going through the discussions. So across the years 5 to 10, you can see that there's a little bit of a scope increase between grade 5, grade 7 and 8, and grade 9 to 10. It does increase in complexity, and the load is gradually increasing over the years. Planning to teach. The content descriptions within the curriculum provide explicit statements about what needs to be taught. And it's up to the teacher and the school to organise the content into coherent and effective learning and teaching sequences to suit their school. Every school is unique, so the flexibility is there for them. The next thing that the curriculum provides are the elaborations. They're ideas rather than specified items to be ticked off. They're really good to bounce from, to develop a plan to suit your own context. But there is no need for you to address every single one of those elaborations. They are thoughts and ways that the content might be addressed. So firstly, let's look at years 7 to 8. So we have the achievement standard here for digital technologies. And this is what they need to achieve by the end of year 8. So we have the 2 years to get here. It's always informative to know where we must finish. And the best way to do that by reading perhaps the first sentence, which summarizes all the information about where they the 2 years. It sums up the achievement standard. So the differences between 8.4 and 9 in year 7 and 8, the differences in producing and implementing, is you can see on the right there in version 9, we have the addition of the word debug. So we still keep the word implement, modify, we're adding the word debug, which really does clarify what we expect students to do along the way.
Okay, thanks, Kylie. So when we talk about implementation, what does that mean? What does the curriculum expect from that? It's really just applying your algorithm as a program. So basically coding it effectively. And this is taken from one of the supporting documents from the curriculum. So here's an example of what we mean by implementation. We've got an algorithm in pseudocode on the left, and then we've implemented it in Python code on the right. Okay. And we notice that in this particular algorithm, there's a loop, the for loop, inside an if-else block. This is called a nested control structure. And we'll talk a bit more about that in the next slide. So nested control structures are new to V9. I'm not saying that they're new to teachers. I'm sure you have used nested control structures. It's just explicit that we're expected to teach them now. So the definition of a control structure, you probably remember, it's sequencing, branching, and iteration. And they're the basic building blocks of any algorithms. Nested control structures are when you place one of these control structures inside another one in your sequence. So for example, you might have an if-then statement placed inside a for next loop. In this presentation today, we're going to focus on how we implement them rather than the designing of the algorithm side of it that we did last week. So in that previous example, we had a for loop. You can see there's a for loop inside an if-else. And it's saying if there are digits, for each of the digits, do something inside that block of code. Else, on the outer block of code, we have the list, print out the list is empty. So you have a concept of the inner loop and the outer loop when you have nested control structures. Here's some examples that my friend ChatGPT came up with of different variations of control structures. So you could have an if inside a loop in the top. You could have an if inside an if block. So that's a nested if. And there's a couple more. You can have a loop inside an if. So for all the friends in the friends, provided you've got friends, hopefully you do, then you print out, make more friends. So we have this language, which is the outer loop and the inner loop. Okay. And in our Grok courses, Billy agrees with me, by the way, that's my little Labradoodle. In our courses, we have decisions within decisions. So in the Grok courses, this is from our Python for Beginners course, we've got an example of how nested if statements work. So this is just showing you that if you'd like your kids to sign up to the Grok course, that we will cover this part of the curriculum. And again, in the same course, we've got another example of a nested if, which is fairly common. You know, if you want to do anything interesting, you're probably going to be using nested ifs. Okay, in terms of implementation, how could you get your students to implement this? You might use the NCSS challenge, which is a Grok challenge that goes for several weeks and your students can sign up to, and it sort of teaches them as they go how these things work. So you've got the 3 levels: beginner, intermediate, and advanced. You can get in touch with us if you want to know more about the NCSS challenge. Another way that is really well suited to teaching nested control structures is a text-based adventure game, which we have mentioned last week. And here's an example of an assessment that I think I might get Kylie to explain.
So with assessments, it's always really good to make sure that you've got a background to the task. Students have got a purpose and they've got a reason or an audience for who they're projecting to. So, for instance, if they were doing a text-based adventure game, it might have a purpose such as keeping young people safe online. So that would be the assessment task. And within the assessment task, sometimes it's really good for you to scaffold. So there's some scaffolding links on the next page where you can break up the task so that it satisfies your criteria that you're trying to address so that students don't miss it. So we don't want them to miss the designing stage where they use flowcharts and pseudocode, one of those, to communicate their algorithm, that they make sure that they include nested control structures and that they make sure that they have modularization, because functions or modularization is part of the 7 to 8 curriculum as well as the 9 and 10. That they validate, that they implement the program, and that they modify and debug along the way. So it's explicitly asking them what they need to do. An example on the next page is a rubric that might address the adventure game. So you would have some generating and designing being satisfied and some producing and implementing. And in italics there, we've noted some of the items for which you would be looking in order to some of the evidence that you would be looking at along the way for the students. It's always nice to have a look at how you might assess tasks along the way. So for years 9 and 10, things change a little bit. Again, we've got the achievement standard. And by the end of year 10, students develop and modify innovative digital solutions, decompose real-world problems, and critically evaluate alternative solutions against the stakeholder stories. So that one is another step up again from the year 7 to 8. And it gives us an idea of where we're heading by the end of the 2 years. So last lesson, we looked at flowcharts and pseudocode. This week, we're focusing on implementation. However, we do note the differences between version 8 and version 9, that logical operators is also included. So we're going to include those while we go through implementation. And the differences between version 8 and 9 in implementation, as you can see there, the debug is included. So that's something that we probably need to spend some time looking at today. So Sarah, I'll let you take them away with logical operators.
I love talking about logical operators, Farley, so I'll get stuck into this. So what is a logical operator? So basically logic, it's a whole area of computer science, and we're just looking at a small part of that. And an operator or function to combine Boolean true or false values, including and, or, and not. It's actually not that complicated, but it does sound complicated there. You've actually used these before. Whenever you've used the word and, if you were saying like both X and Y are true, and we use it in language all the time. So here's a pseudocode example to maybe make it a bit simpler. If the temp is above 30 degrees and people are inside the building, then open the windows. So the logical operator there is the and. It's how you're combining two statements to basically get a true or a false out of it. We also, in the curriculum, there is mentioned the word Boolean operators. They're used interchangeably with logical operators in the Australian curriculum at this level. A Boolean is something that is either true or false. It's a data type, like an integer or a string, and it can only have two values. And we can combine Booleans using Boolean operators or logical operators. So for example, A and B, true if both A and B are true. For example, it's raining and it's cold. Or we have it's raining or it's cold. Only one of them has to be true. And the not logical operator, that works on a single statement and it just makes it the opposite. So if it was raining and you said it's not raining, you've got the opposite condition. This comes a bit more clearer when we look at code. And this time I've included an extract from a different Grok course called Introduction to Programming 2, Python. That's where students would do that course once they've finished the Python for Beginners course and they're ready for that. And one of the examples there is with and or. So this is really just an example to show you how and or works. So if you say print a less than 3 and b less than 5, that's a true and a true. So a true and a true makes a true. Okay, I don't want to get into too much details about this, but you can go and explore that course if you want to know more about that. And remember, this is at a year 9 or 10 level, so it is a bit more complicated. If you're a 7 and 8 teacher, you don't have to stress too much about this one. Okay, let's move on to debugging, because this has been introduced in both 7 and 8 and 9 and 10. It's not that you didn't do debugging before. Now it's just explicit that teachers must teach the process of debugging. And this is a really important skill in programming. So the top level statement, that's the year 7 and 8, producing and implementing and the changes. And also the bottom is the year 9 and 10. And both of them have debugging explicit. So what is debugging? Well, a bug is the name that's come up with when you've got an error in your program, meant to be attributed to the discovery of an insect in a computer. Maybe that's a bit of an old wives' tale. We're not sure about that. So debugging is just finding and solving the bugs in your program. And this is really related to the general capabilities, where we want students to learn to think critically, to break down problems in the process of understanding their code. So these skills are really important. Here's an example program, and there is an error in that. There's a bug in that. It looks pretty nice. There's a little function. However, there's missing something there, and that's the return statement. You can't get that. That would actually crash that program. So that's just an example of a little bit of debugging there. So we've just got some strategies here. These aren't definitive, but these might be helpful for you when you're teaching programming and debugging. So number 1 is learning to read and understand the error messages. The language gives you error messages. Sometimes they're hard to understand, but you can train the kids to get better at them. Second is use print statements, and this is really a really easy way for students to understand what's going on in their programs. A third way is tracing through the program. We mentioned trace tables last week, and this is actually a part of debugging. And fourth is simplify the program. Just encourage students to write simpler programs. Then when there's an error, it'll be easier for them to work out what's wrong. Chunking is a really good way to debug, where we basically ignore a lot of the program and just hone in on each error at a time. I'll spend a little bit more time elaborating on each of these steps. So the first strategy was read the error message. Okay, this is a Python error message that we're focusing on Python this session. And it isn't that easy when kids first see this, but if you explain to them that it tells you where the error occurred and where it's most likely to have happened, and that syntax, this is a digital literacy exercise here. They have to understand the language that the Python compiler is speaking in. So they have to understand syntax means usually is something with the way you've written the words. Okay. Here's an example over here where we've got a different error message. This is index error, string index out of range. And this is a common thing with arrays in Python. They index from 0. So they start at 0, 1, 2, up to the length of the string -1. And this is just a part of the process of teaching your kids how to understand the error messages. Print statements, this is fairly obvious. You just get them to put a print statement where they think the error might have occurred. Then they run their program and they see what information that tells them. So here we've got the similar error with the index out of range. If they wanted to work out what was going on, they could put this print statement on line 4 and a print statement on line 2 telling them how many characters are in this string. And then when they see, oh, there's 4 characters, I've already done them all, I've got up to 4 and it's freaking out. Okay, so that hopefully that would ring a bell in their head to say, oh, I remember, that's right, in Python they start from 0. Tracing is a third strategy we recommend. So with tracing through the program, I often say to the children, step through it in your mind's eye. Imagine yourself going through the program. Or if that's too abstract, get them to explain the algorithm to another student or a duck. It's known as duck debugging in the industry. Although I can't actually say I've met any software engineers that talk to ducks while they're working. Another way, I mean, Kylie was saying last week about designing using pen and paper. Trace tables are great with pen and paper as well. They just simply write down what all the variables and what their values are at different points of the algorithm. Or we can go sophisticated and use a visual debugging tool either within an IDE. For example, if you've used Visual Code, there's a debugger built in. It does take some skill to learn how to use a debugger, but that's achievable for maybe for year 9 and 10. Or there's a website, pythontutor.com, where you can simply copy your code, paste it in there, and it will step-by-step run through the code.
To use Python Tutor to visually trace Python programs, simply go to the website https://pythontutor.com and select Python, and then copy and paste your code into the input box that you want to visually trace, and then click the Visualize Execution button. It brings up the code now with a little red arrow pointing to the first line, and that's the next line to execute, and once we've executed a line, it'll go green. Now it's waiting for input, so let's type my name in, see if I can spell my name. And then it's gone to the next. You can see the line has gone green, and it puts the output over on the right-hand side. Now it's going to go to the next line. So this is really helpful if you're trying to debug and find out where your mistake is happening. My name is not Alice, so it's going to go out there and print, "Hello Sarah, nice to meet you." Hopefully that helped you work out how to use Python Tutor for debugging.
Step 4 in our debugging strategy recommend is simplify the program. This is really important in getting the students to use meaningful names for variables and functions, because when you come to debug it, if you have weird names like X and R and I and just single letters, it's going to be really hard to debug. So for example, a meaningful name like number of steps versus the letter N. Use comments. Comments really help kids debug because they can see what's meant to be happening rather than what code they put in. And also going back to the rubric that Kylie mentioned before, commenting, I think, should be worth marks or should be worth something in when you get students to submit assessments. The third step to simplify is split complicated operations, especially when you're nesting functions. Really make sure your indenting is right and put them on separate lines if possible. If you have a compound statement like a Boolean operator, you can actually put the logical operator on one line and the rest of the statement on the next line. Make sure you use a consistent style. Don't mix your variable name types, like sometimes use camel case and sometimes use the underscore. Just having consistency really helps. A final strategy is chunk the program. And what I mean by chunking the program is that often you've got several different errors. Try and focus on one error at a time. And where you can, comment out parts of the program that aren't needed to debug that particular error. So often I would do that, which is comment out a whole bunch of functions or make them just return a dummy statement. Okay. So hopefully these techniques have helped with the debugging because it's very important. We've also got a Grok course that you can enroll in, which goes through some of the common bug debugging errors that people have and gives your students a chance to practice with that. Okay, so we've talked a lot about implementation. Now we want to sort of give you some more tips about how to teach this implementation to the students. We're going to describe two common pedagogies, Prim and Parsons puzzles, that may be helpful for you. The challenges with teaching programming are many and varied. If you've done that, you'll know. There's timing. It takes students to work on writing code. Misconceptions is a really big one. For example, assignment, letting one variable equal a value. Sometimes kids just can't get the order of that right. They mix it up with maths algebra concepts, for example. And we don't want students to get into a spiral, so we really want to scaffold them as much as possible. And that's really what these pedagogies that we're talking about today will help with. The first one we'd like to talk about is PRIM. That stands for Predict, Run, Investigate, Modify, Make, and it's developed by Dr. Sue Sentence from Raspberry Pi Foundation. And the Raspberry Pi Foundation has a great website with lots of programming resources. So this pedagogy aims to help teachers so that they have a structure when they're teaching programming. What is it? What is PRIM? It basically breaks it up into sections where the students don't have to start from scratch. They can look at an existing program, predict how it's going to work, then they can investigate what happens when they make changes, and then you can tell them to modify what you've done, then make their own from scratch. And it reduces the cognitive load on the students because they don't have to start from scratch, and it's not so overwhelming. The first phase is predict. Basically, you just give them some code and you say, what do you think is going to happen? It really gets their critical thinking skills, again, back to the general capabilities, that they have to think about what's going to happen. There's not much pressure on it. They can guess. Doesn't matter if they're wrong. For example, here with this bit of code, you would say, what do you think the output's going to be? And here's some possible things students wrote. They won't get in trouble if they get it wrong. Yeah, so that's the idea with the predict phase. They learn to read the code with the predict phase. We can clarify some misconceptions at this stage. The next stage is the run stage. We then compare the predictions against the actual program output. And then these students now can correct their misconceptions at this stage. They confront their misunderstandings, and it gives them a talking point to, they feel some ownership because they predicted it. And here you can see an example of what might have happened. I didn't know that was a variable. I wasn't sure what set word is. We're getting our language here, and they're starting to talk about code. Once they've done the predict and the run phase, the next phase is investigate. And here we can do learning activities that promote code comprehension. This might be tracing that we referred to in the debugging phase, or we might get to be doing pair programming. We might get them to annotate code, anything that sort of promotes investigation of the code. Now, once they have corrected their misconceptions and done a run, a predict and a run, now they can actually modify things. You might get, if you're teaching them microbit, you might get them to display a different shape on the screen, or change the background of a game in Scratch. The final output should contain 2 names, not just you. So we're just getting them to do a little tweak on the code, so we're building up their capability in a scaffolded manner. The final stage is make, where there's no scaffolding at all, and we let students apply their understanding to a new problem. Okay, so that was PRIM. Now, one final pedagogy that we'd like to talk about is Parsons problems. This would help with the implementing phase of teaching algorithms. Parsons problems or puzzles are a way of writing programming problems where students rearrange fragments of code in the correct order. So we give them a piece of code, but we jumble it up like a puzzle. That's why it's called a puzzle. And they can help students just by rearranging it. They don't have to start from scratch. Again, this reinforces the PRIM idea that we're starting from something and we don't have to write. It's sort of like in English where you don't want them to write a whole essay from scratch. You might get them to write little fragments of writing. These are particularly good, I think, for teaching the control structures that are new into Year 7 and 8. Grok has some Parsons puzzles in a small number of their courses, but you could make your own. You could even use pen and paper or Google Draw. There is a free tool that we recommend. hackmd.com/Parsons is where you can find that. And that was adapted from another site. So here's the example of the that hackmd.com, and this is what the website looks like. You put in the title, your name, and then you put a description of the puzzle if you'd like to share it with other people. It can be helpful, and you can look at other people's shared puzzles. Then you put your code in down the bottom. And then now you can preview your puzzle. It automatically generates a puzzle chunked up to things on the left-hand side that you can drag across to construct the correct solution. So the students have to drag it across, and they have to include indenting if it's a Python puzzle, for example, and they have to get it in the right order. But it's fairly, you know, they can try and they can test it out. So they're not going to get in trouble if they get it wrong, basically. And here's an example. They dragged them into the wrong spot and they got an error, and it actually tells you that you've got an indentation error, and it will tell you that it's not in the right order. And they finally got it right. So they had to get the branching right, and they had to get the if and the else. You can see that it is give practice in control structures. So that concludes our discussion for today. I'd just like to talk to you about some resources for further reading. There's some general resources there. There's some specific PRIM resources if you'd like to know about some of the research into that. And there's also research about Parsons puzzles. We always recommend that you do not be afraid of pen and paper or unplugged algorithms. And these are some links to some Grok unplugged algorithms that you can use for teaching algorithms. And then there's the online courses that I mentioned, Python for Beginners. Then there's Introduction to Programming 2 Python, which would be the next step. There's also a really nice course, which is more an integrated course, putting together biology and science and classifiers that we recommend. It is slated for as Year 7, but you can extend that course. There's also an assessment for Year 7 and 8 called the Gauntlet of Riddles that we have prepared if you're interested in that one. And that concludes our session for today. And the next session after this one will be privacy and security. Thanks very much.
Lovely. And for those of you who might have missed the announcement, as of 4th of October, we've got a 5-year partnership between Grok and WiseTech Global to make learning digital technology skills available to every Australian student, teacher, parent, and adult learner for free. Grok's mission is to educate all learners in transformative computing skills, knowledge, and dispositions. The partnership with WiseTech removes the financial barrier for schools in using our resources, as well as allowing us to expand our team to continue to support schools, teachers, and learners. Thank you so much for today. We've enjoyed bringing Algorithms 2 to you, and we look forward to seeing you next week for privacy and security. Thanks very much, Sarah.
Thank you. Thanks, Carly.